Now then we will start. And good morning, everyone. And thank you for joining us today. I am the MC Xiaying. Before the distinguished lecture starts, may I invite all of you to rename your Zoom discipline name to Name Institute to facilitate today's discussion, and use chat and raise hand functions for posting questions during the talk. Mute your microphones while not speaking. There will be group photo screenshot later. Now let's invite Professor Kenny Liang to give an introduction about the Sticky Lab of Marine Pollution. Professor Liang, please.
Thank you, Dr. Xiaying. I would like to welcome all of you to join this SKLMP Distinguished Lecture Series. I can see many of you from different parts of the world. I can see some from Southeast Asia and also from mainland China, and also quite a lot of our members from different universities, and also our research students and research staff. Welcome to join this wonderful lecture. As you may know, due to globalization, there are more marine traffics and marine merchants events happening. And the global tonnage for these shipping activities increasing in an exponential manner over the past 20 years. And then this also go hand in hand with the oil spills incidents around the world. And also, there is a high demand for this fossil fuel, and then many of them actually come from ocean. And then you may know many incidents happening in the oil drilling platforms around the world. So Hong Kong is not alone in the business, because we have many marine shipping industries and also marine vessels going in and out Hong Kong. Almost every year we have reported oil spills in Hong Kong or adjacent water. And oils come with different forms. They will have a different persistency, different toxicities, and also now with the technology advancement, and then we are able to control them, tackle them in a more effective manner. Today, we are very, very happy to have Professor Chen, a world-leading expert in oil spill monitoring and also control. So he will tell us a lot of latest advancements and also experience from Canada. So we're going to learn a great deal today. So before I hand over back to Xiaying, I would like to share two good news about our laboratory. The first good news is that our government has just confirmed that we will receive a double of funding on annual basis. From 10 million per year now, we will start to have 20 million Hong Kong dollars per year. So this is a fantastic news. That means I can give out more money to support your research and also buy more fancy instruments to help our research. Second good news is that yesterday we got a formal approval from this intergovernment organization called the Partnerships of Environmental Management for the Seas of East Asia. The Seas of East Asia, correct? And in short form, it's called PEMSEA, PEMSEA. So they confer or granting us the status as the regional centers of excellence in marine pollution. So we are one of the 4 regional centers of excellence in PEMSEA. We have a great honors to serve the region in the whole East Asia. So we're going to offer a lot of training opportunities as well as research projects across countries in this region. So then I hope more good news to come in the near future. Once again, thank you all of you to joining this lecture. Most importantly, thank you, Professor Chen, for being our honorable speaker. So thank you very much. I pass to Xiaying.
Thank you very much, Professor Liang. Thank you for providing us those good news. And now, could you please open your camera for taking a group photo? All the audience, please open your camera, and Sarah will help us take the photos. Sarah, would you mind let us know when you're ready?
Okay.
Are you ready to?
Not yet, because there's not much people turning on their camera.
Oh,
So
no, we can wait.
I'm still waiting for them.
Okay.
Ladies and gentlemen, please turn on your camera.
Please, yeah, open your camera.
I think I will start taking the photo right now.
Okay.
So ready, 1, 2, 3. And the second page. Ready, 1, 2, 3. The third page. Ready, 1, 2, 3. Okay, thank you so much.
Thank you.
Thank you, Sarah.
Thank you.
Now, let me introduce our speaker, Chair Professor Bing Chen. Professor Chen is U-Arctic Chair in Marine and Coastal Environmental Engineering, Professor in Civil Engineering, and Associate Dean of Faculty of Engineering and Applied Science at Memorial University of Newfoundland, Canada. He is also the director of Northern Region Persistent Organic Pollution Control Lab, or called NRPOP Lab, and the director of a global network on persistent, emerging, and organic pollution in the environment, where it's called People Network. Professor Chen has developed novel engineering and managerial solutions through integrating environmental engineering with nano or biotechnologies and advancing physical and numerical modeling methods. He has authored over 470 technical publications, including journal papers, books, as well as patents. Professor Chen is a fellow of Canadian Academy of Engineering, Engineering Institute of Canada, and a Canadian Society for Civil Engineering, and a member of Royal Society of Canada and European Academy of Sciences and Arts. Today, Professor Chen will give us a speech about marine oil spills, lessons, challenges, and new advances. Professor Chen, please.
Okay, thank you very much, Dr. Xin, and also thank you very much, Dr. Liang, and also other colleagues and students here. First of all, congratulations on it's not a good news, that's great news. I feel even jealous, right? $20 million per year, that's a lot. You know, that's, I think, also the Excellence Center of Excellence that's really promote the research collaboration and training of students. I think as a students, you feel so lucky, you know, to associate with such excellent organization, right? So that's a great future, I believe. Okay, thank you again. And it's really my pleasure to give the talk. So let me share my screen. Okay, so now I assume you can see my screen. Any issues?
We can see that.
Okay,
No
great.
problem.
So my voice, no problem. The video.
Yes, great.
Okay,
Yeah, great.
Great, perfect. Okay, so let's talk about the marine oil spills. Thank you again for the invitation and also kind of introduction. So I'm a professor working in the marine and coastal environmental engineering this field, especially because Memorial University, the location is in St. John's. That's the most eastern part of Canada. It's facing to the North Atlantic. And also our province, another part we call the Labrador. You may know Labrador dog, right? So the origin is from Labrador. And that's where we're facing the Arctic. So we have quite unique position facing two oceans, and with growing pressure or stressors from human activities on those ecosystems in the marine and also coastal environment. So today let's talk about marine oil spills. And we know like just a few minutes ago, I talked with Xiaying regarding the weather. So when people talk about Canada, always think, okay, snow, ice, polar bears, right? So, but we do have beautiful summer. Like in the past week, we got more than 25 degrees, and most of the day that's over 30 degrees at noon. And even there's a record of 36 degrees, I think last Wednesday. Obviously, we become warmer than the past, say 10, 20 years ago. We have less snow comparing with 20 years or 30 years ago. So that's we are facing the definitely very clear evidence showing the global warming obviously climate change. So of course, because I think globally we are working hard to fight against the global warming and especially reduce carbon emission and try to use more renewable and green energy. However, our world still being driven mainly by the oil and gas. And here I have a figure showing in the near future, at least by 2025, the petroleum and also the other liquids, including biofuels, will be still the main driving force, plus the natural gas. And the increase probably around 40% next 20-25 years. So that's very similarly trend happening in Canada. As you know, Canada producing a lot of oil and gas as one of the leading producer and also exporting oil and gas globally. And the two major regions in Canada producing oil. One is the prairie, like Dr. He originally came from in Saskatchewan, Alberta. That's inland oil spill. Inland oil production. And then Newfoundland, Labrador. That's where I'm located. That's offshore oil gas production. So that's the Eastern Canada. So you see the trend is still growing. We'll produce more oil for sure to meet the growing needs, the population, the quality of life, of course, producing more greenhouse gas emission, unfortunately. On the other hand, we, as an environmental researcher, we're always looking at the environmental issues. From the first day of oil and gas industry, we already had oil spills, from minor ones to the major ones. The spills came from, marine and coastal oil and gas operations, like from the exploration, production, refining, utilization, transportation, and storage, right? From the tankers, from the platforms, from the pipelines, or even the boat, right? Every boat, even the fishing boat or passenger boat, they carry oil, fuel oil. And if there's, especially because the accidents, and you look at the timeline, I give the pictures and the examples here. If you check easily in Google, almost every year we have major oil spills. Talking about major, more than 100 tons of oil spilled. And according to the OPEC reports, 1 billion gallons of oil spilled. And 6 million tons per year enter the ocean. 5% that came from the oil spills. That's huge. So that's the major oil spills caused catastrophic damage to the local economy, the tourism, the shipping, the harbor, the oil and gas industry, and also of our marine ecosystem. That's a long-term significant adverse impact, and take years, even decades to recover. So to respond spill, we're basically fighting against the time, conditions, and the consequences. Here I give you a few examples. The first one, probably the largest one in human history, was not because of the accident. That was, unfortunately, it's elaborate. It's during the Gulf War. So the spilled oil result in around 4-inch thickness of oil slicks, cover more than 4,000 square miles in the Persian Gulf. And the next one example is very infamous example. When people talk about environmental pollution, especially oil spills, always this is the one referred to. The Exxon Valdez spill, that's in Alaska of US. And that one, because of the grounded tanker, released 11 million gallons of oil and killed, more than 250,000 and seabirds and 3,000 sea animals. And that's already 30 years past. And because of that's in cold region in Alaska, still, if you visit there, you still can find oil residues there, tar balls in the sand buried. You see, that's how slow the nature will self-clean themselves. And that's already through a very expensive, costly cleanup actions for several decades. And the recent example, BP oil spill, all we call it as a deep water horizon oil spill, 2010. That's because of the blowout, operation by a Mexican company and using this BP facility. And then oil ignite and it cause explosion, kill people right away on site, and release oil. And the oil gushing out at a rate of 10,000 to 3,000 barrels per day, last for a whole year. And we know those numbers easily you can find from the news. And you see this talking about 4.9 million barrels. Barrel is a very commonly used unit. It's 1 barrel is 42 US gallons and 159 liters or 0.38 metric tons, roughly. So you can put in this way. 1 barrel, the volume is basically a standard bathtub you used at home. So the bathtub is roughly 1 barrel, 24 US gallons. So that's, we are talking about 4.9 million, the volume, the bathtub of oil filled with oil dumped in the ocean and cover 10,000 square kilometers and kill 1,000, even 30,000 birds, 6,000 sea animals. And the liability in total, the estimated liability more than 100 billion US dollars. Now, that's including compensation, clean up, and also the loss in the stock market. And that was claimed by the President Obama at that time. That was worst environmental disaster in U.S. history. And also it's not a single event that lasts a long, long time. Till now, still people clean the residues up along the coast, Gulf of Mexico. And the problem is spills continues. Even during the pandemic, right? People got break or work from home. We have spills going on. Because we still need energy. We keep the wells producing oil, tankers, pipeline transporting oil, power plant, our home using oils, so the spills occurs. Like from the Brazil 2019 to Russia, that's very close to the Arctic Ocean, and also the in Canada, in BC, very interesting, that came from a sunken vessel already 60 years ago. And also the oil spill in California, Southern California, and from underwater pipeline. And the recent one, Peru oil spill, that's because of the high wave caused an explosion during the unloading from the tanker to a refinery nearby Lima. So that's part of, like as claimed by the government of Peru, that's a kind of ecological disaster. It's not because of the high wave caused by a tsunami from thousands of miles away. So that's also that's indicating accidents, more accidents or more higher frequency because of the extreme weather cause accidents from the tankers to platform pipelines and causing oil spills. And I usually put these two pictures together. So BP oil spill, box of Pandora. And human being, we open the box of Pandora, release the evils. Of course, oil and gas is not only create problems, they also bring a huge amount of money, drive the economy. And where's the hope? Because we know the myths tell us that also hope came from the box of Pandora too, right? So, but as a researcher, I think we will help people and the government to find the hope. What can we do to fight against the marine oil spills? And here's a figure I always use that's produced by a panel. I was part of the panel of the Royal Society of Canada. That's 7 years ago. We published a book that's more than 460 pages, as I recall. This is this book already become a milestone, and a lot of use of citations, and especially this figure. I think that's probably most comprehensive figure in the, showing what happens after oil spill. It's quite complicated. This is why oil spill is challenging. You see, I don't need to cover every part, but the major process after oil spill, you see through the waves condition, the oil slicks spreading, and even to the coastal region, and some oil dispersed, dilute, and also sink to the bottom in the sediment and maybe released in the future. And also uptaken by the fish, by the plankton, and also caused because of the mineral particles there, so that leading to aggregates, and especially those oil can be pushed by the wave or the current to the shoreline and create more economic disaster. And of course depends on the property of the oil. Some oil part components will evaporate and also create some because of wave action, they'll cause aerosols, and also photooxidation, biodegradation all happens. Especially when oil touch the sand or gravel, that will create aggregates. That's a more challenge to clean them up. And in Canada, in northern ocean, we have sea ice. If you have ice, means the oil could be stay on top of the ice or beneath ice or inside ice. Ice is melting daytime and frozen again nighttime. So trapped oil. So all those things happens, and how to clean them up. That's really a big headache. And this is why it will take a long time, and also millions, even billions dollars to clean them up. that report already that's published online, so that's free. You can download easily from by Google and the Royal Society of Canada Oil Spill report. Two other figures I'm showing here. One is showing the actually indicating some opportunities. You look at the visering process of the oil after spill, and in the talking about hours and days, the evaporation, dispersion, or the dissolution, emulsification, spreading, they take the major role. And later on, after weeks, even years, biodegradation, sedimentation become more important, especially biodegradation. So that's indicated opportunities and how we can improve the dispersion, the oxidation, the biodegradation. And also because of the oil properties, we have different groups of oil. It depends on their gravity or API value, right? So we have light oil and like gasoline, jet fuel, and they evaporate quickly. And you see the figure within hours. And then we have the marine diesels, they are heavier, and then even dialbate, the Terra Nova, like from offshore Newfoundland, and also even to the really heavy fuel oil and the bitumen, they will stay there long time. So that really depends on the oil properties and also the conditions. And how can we do to deal with oil spills? There are a list of measures we can use. We call the oil spill prevention, control, and countermeasures, SPCC. From the prevention, that's the best way. We should prevent oil spill from happening through a better management, monitoring, better facility, etc. And also we should get people prepared, from the workers to the managers to the decision makers, stakeholders, the public. We should get ready. If there's oil spill, what can we do, right? Following the plan. And also we should have comprehensive real-time surveillance and monitoring and tracking systems, and cover the ocean, cover especially the harbor, and also the sensitive areas like the ecological reserve, and also surrounding the platform, and also the basic shipping routes, right? And collect the data and how to analyze that, especially using the AI tools. Now it's more available. And also we need to using the modeling tools to simulate where the oil come from and where they go, right? So, and then we evaluate the impact and risk, and then we develop a response plan, make a decision, and take actions. So then they're talking about the recovery and cleanup operations. And after the event, we need to reevaluate and improve our system and our technologies and find the problems. Talking about the technologies, especially for recovery and cleanup, our laboratory have developed a set of different technologies. And here is in general, from the natural attenuation, that means you leave it as is, let nature clean them up, right? And also through the visering process. And then we have the physical recovery, especially like the in situ burning and booming, herding. The boom, we use the boom, like the picture showing here, the orange or red color. We use the boom and collect oil, herd oil together, and either if reach the thickness, like for higher than 4 millimeter, we can burn them. We call the in situ burning, cause of smoke for sure, but that's quickly remove oil. And also we can do the skimming, and using brush, vacuum, or drum skimmers, we can skim the oil from the top of the surface. And then we can treat the skim the water, and we call it decanting. And then if the oil reach the shoreline, we need also use some manual or mechanical oil removal measures, vacuum, flooding, or flushing, or washing. And then we use we have a group of chemical compounds we call treating agents, like dispersants sprayed by the airplane or the responders, and also like demulsifiers, washing agents, solvents, solidifiers, and then we can use biological methods, biostimulation or argumentation. So that's the the package of the technologies we can use. There comes with challenge, and like according to the report by the submitted to the United States President, the BP oil spill claimed as the whole country awfully unprepared. That's the heavy lesson learned. And also in Canada, similar thing. After the BP oil spill, that's a big view, and all the governments, industry reviewed their capacity. And unfortunately, people found, okay, like for example, the Minister of Canada talk about the whole country is not ready at all for the major oil spills. And a similar thing, recommended by our report, Royal Society of Canada, also we call urgent call for advanced research and the applications. And there's a lot of challenges. Of course, those technologies already been there for decades, but we have new problems. And also some situations we never think about that before. We urgently need the new technology or improved technologies like monitoring, early warning, and more green or eco-friendly, efficient treatment or robust cleanup technologies, and modeling, spill modeling and decision making, especially real-time dynamic decision making. That's the need. And talk about the environment, the harsh environment, the extreme weather conditions because of the climate change, cold weather, cold water, and sea ice, rough sea, low visibility. So how to deal with spills during that time. And there's, of course, opportunities, always comes with challenges. The funding, and also there's knowledge and technology gaps. And, we have very limited research and development, especially for some harsh environment and the deep seas. And the whole, the society, the industry moving to north and to deep. That's the trend. But are we prepared? That's a big question mark. Funding opportunities, like the BP oil spill, after BP oil spill, the BP company and also government put in more than $500 million US dollars for oil spill research. And in Canada, similar thing, back to 2016, there's first a national oceans protection plan, and invest more than 54 million Canadian dollars, and for 4 years projects, I was part of that, also a national advisory committee member, and that's just closed this year. And very luckily, recently I was informed the second version of the Ocean Protection Plan just ratified by the Parliament. So we are going to have another round of funding opportunities for oil spill research. That's really excellent news for researchers. Now, since I already gave you some background and my understanding of the challenge and opportunities about marine oil spill research, and now I'm briefly talk about our laboratory and also what we are doing in recent years. The laboratory we called Northern Region Persistent Organic Pollution Control, NRPOP. So we hope it will become popular, right? So NRPOP. That's the first of kind targeting the persistent organic pollution, especially oil spills and the emerging contaminants in the northern region and also marine environment. That was founded back to 2007. And that was supported by the national and also provincial governments like UNSTRC, CFY, Newfoundland government, PRL, industry. And our targets, the two groups. One is the persistent and organic pollutants, oil, hydrocarbon, and especially those like a pH and different waste streams from produced water, ballast water, oily wastewater. And also another group is emerging contaminants. and from the micro or nano plastics to PPCPs and artificial nanomaterials, etc. And the environment, we're talking about the cold region, North Atlantic, Arctic, subarctic, and the marine and coastal environment. So we have over 15 core and associate professors, including adjunct professors, and we always have 20 to 30 graduate students and plus postdocs working in our lab at any time. And we have global collaborations, and from Europe, America, and Asia, including China mainland. And hopefully we can develop a collaboration with you in Hong Kong. And I'm quite proud of our facilities, not only our talented people. We have some quite unique, I should say, we are probably in Canada, across country, our lab in the university, we are the most comprehensive lab hosting the facilities to study oil and also the emerging contaminants. Like we have the whole fleet of the analytical tools from GCMS, GC, MS, HPLC, MS, AS, TOCs, etc. And also we have instruments for nanomaterial, nanotechnologies, and also biotechnologies, and along with softwares. And very importantly, we have very good facility for physically simulating the oil and also pollutants transport and fit. And like we have not only our lab, that's our university, we have the very huge wave tank, and also have the largest ice wave tank, talking about -30 indoor. And very recently we create this new facility. It's an indoor oil spill R&D facility, and that's first in Canada. And that's including a 14 meters long wave tank and also 3.6 meters long soil tank. So we can study both marine oil spills and also inland oil spills. The research approach, here we only focus on oil spills. Actually, our lab doing other research and targeting from the river, lake to ocean, groundwater, soil, and from wastewater to solid waste. And the major tools, one is traditional environmental engineering tools, like the advanced oxidation. That's one of the major tools we're using, to the nanotechnology and biotechnology. And also we're using modeling tools from the assessment, simulation, optimization, decision making, and AI. And the target, again, that's the hydrocarbons and the emerging contaminants. So talking about oil spill research, we have basically covered 5 major areas, and there's some new topics emerging. Let me introduce them one by one. And because I'm present here, they're all published. I think if you miss any information or you're not very clear, you feel free to let me know. I can send you our papers. And we already published more than 100 journal articles in oil spill related research. And the first area, talk about the Bowel Surfactants. So Bowel Surfactants is a group of compounds they produced by the microorganisms naturally, and they are producing, they can reduce the surface tension. And you look at the figure here, basically that's a compound, that's the rhamnolipid lipopeptide, and so they're basically a big head and a tail, a long tail, right? The head is hydrophilic, and all we call it as a water-loving head, and they also have a water-heating tail, we call it hydrophobic. So when the water-loving head is surrounded a water molecule, they can drag the water into the oil, so cause an emulsion. That's force of Missler. On the other hand, if the water heating tail surround like an oil molecule, then they can drag the oil into water so dispersed oil. So that's provide a multi-function. So this is why the bowel surfactants is really interesting and valuable. More importantly, comparing with chemical surfactants, they are none or less toxic and very efficient and sometimes more effective than the chemical surfactants. Like the CMC can increase by 10 to 40 times. It means you need less surfactants to deal with, the pollutants and reach the same results. And also, they very easily adapt to the different environment. Very cold weather, high salinity, or high pH value or low pH value. And also, very importantly, the bowel surfactants, they are biodegradable because they produced by the nature, by microorganisms. They disappear in the nature. That's the key. And why we are studying bowel surfactants? Because in oil spills, we use a lot of chemical surfactants. We call it as oil spill treating agents. They are in like dispersion, in situ burning, booming, steaming, washing. And you look at the BP oil spill. The chemical dispersed, skimmed, burned oil counted for more than 15%. And so that's really the needs there. We want to increase the percentage and recover and all clean more oil. But the problem is when we use those chemical agents, like from the dispersion, herders, emulsifiers, washing agents, we create different chemical compounds. There are growing concerns on their toxicity. Especially, of course, you can argue, okay, comparing with oil, this is less toxic. But still, look at the long term. You use them in the nature, then what will happen after? So that's already raised a lot of concerns. So on the other hand, could we develop something less toxic, even more efficient? Then the hope is bowel surfactants. This is why we developing bowel surfactants. And we collect samples and we screen different surfactant production bacteria. And by now, our lab already have more than 140 bowel surfactant producers. And that's really unique. I think we are the largest, probably globally, targeting oil spills. And we have also something new and newly discovered, or newly reported. And we also using biotechnologies, like for example, UV mutation or genetic shuffling. We can, based on the screened strains, we can enhance them and let them be more robust and more efficient in terms of the eating oil and also producing bowel surfactants. Because bowel surfactants are produced naturally when the bacteria use the oil as their food. And very important bottleneck for bowel surfactants. Actually, bowel surfactants already everywhere. If you look at it, go to shopping, look at the market on the shelf, you will see bowel surfactants. From the detergent you can use to wash fruits, vegetables, to the cosmetic products you use on your face, right? So that's already bowel surfactant there, but very expensive because the cost of the material, the substrate. And this is why we try to find a measure to reduce the cost by using different substrates. Like here, we're developing the technology using fish-based, fish head, bones, and also even the material from kitchen, right? So we can reduce the cost by 10 to 20%. That's really a big improvement and reduce the cost of the production. Also, we try to produce the developed technology to reduce the cost in associated production process or increase the production yield. And we test it through the small scale to a large scale, even using a 100-liter fermenter. And so eventually, like one product we got a surfactant, the productivity is around 1 to 2 grams per liter within 24 hours. That's pretty amazing and quite promising. And our research interested by industry and also funded by United Nations Development Program for commercialization. And we also developed some new technologies to further improve the fermentation, the production. Like we introduced a bio catalyst and also using nano material as a carrier to not providing a large surface and also providing a stable and protective environment for the bacteria to produce bowel surfactants. After we produce the bowel surfactants, and we can develop new treating agents. We call them bowel surfactant-based treating agents or green treating agents. And one is bowel dispersants. We test different combination of bowel surfactants and also from different strains, and along with chemical surfactants and different solvents, and testing the dispersion effectiveness and also the toxicity, and try to identify the optimum conditions and optimum composition of the dispersants. And we tested in the small scale in the lab. Also, we moved to our Fishery and Oceans Canada, the government's facility, large wave tank. And also, past few years, we did some testing in the United States. The on-site facility talking about 200 meters long wave tank. That's basically mimic the real condition in the ocean. And we are going to test in the sea trail in the near future in the Newfoundland offshore area. And also we developing washing agents based on the bowel surfactants, and also for bioremediation. We know like inland oil spills, we're talking about soil contamination. We have the bioremediation, and we can use bowel surfactants to enhance the bioremediation process. And especially talking about the shoreline on coastal region. And we have the small scales and also 3.6 meters long soil tank. We can do both physical simulation, scale down the whole site, contaminated site into the tank, and different layers of soil. And also we can do a numerical simulation to support the development. And we have the sampling and the pores on top and on the side. And also we can use different injection valves to use inject our bowel surfactants. We also developed bowel demospheres, and using the bowel demosifying bacteria, we got it from the Atlantic Ocean, and they can quickly break down the emulsion, because after oil spilled to the ocean, at least in the nature, they very quickly become an emulsion. It's like chocolate mousse cake. Although it's not delicious, it's stinky and dirty, nasty, right? But how to break them? We want to recover the oil from the emulsion. So separate oil and water. So that's the key. And we got very effective results. And you see the picture here. And these herding agents, we also developed bowel herders. You see the video here. On the left hand, there are two paradish. You see on the top, we already how the water and surfactant mixed. Let me see. Is that playing? Oh, okay, playing now. Okay, so then on the bottom one, it's just water. You see when we drop oil on the water surface, create a very thin layer, we call it sheen. And if we already have surfactant there, then they won't spread at all. And on the right-hand side, you see the comparison. And if we have a very thin layer of oil on the surface, we drop a few droplets of bowel herders. They can shrink the oil, increase the thickness, and just a few minutes, you will have a big chunk of oil floating on the surface. So you can imagine if you have this oil slick very easily you can collect them, skim them, or burn them. So that's the magic, power of herder. And we are using bowel surfactants. That's not toxic at all. So comparing with chemical surfactants, the bowel surfactants, they are more efficient and less cost, and more importantly, they're green. They are less toxic and biodegradable in the nature. The second area, we are also developing tools and technologies to monitor and the oil spills and also do the analysis. For example, we not only using the standard analysis measures provided by the government, and also we developing improvement. Right? For example, especially targeting like pH in produced water, very low concentration, how to very quickly, more accurately detect them. And also we're using the biomarkers. Because of the biomarkers, like our fingerprint, they're quite unique for different oil, different well. There's no identical ones. So this is why we can use biomarkers to trace, the oil, where the oil come from which well. And also we can understand, because the biomarkers, they are really resistant to biodegradation. They all stay there for a long time. So easily you can use them to understand the transport fate, especially the biodegradation pathway. We also use isotope and along with biomarkers to understand the vacuum process of the oil, especially for the oil after application of dispersants, including chemical dispersants or bio dispersants. And we also developed the PIFA-based analysis tools, especially want to look at the change or shifting of the microbial communities, because the stressors as oil, spilled oil, the oil really can change the microbial community, the composition, the strains, and they'll help us understand the impact. And also on the other hand, we can help us to screen out the robust ones, and they can survive in the oily condition. Another important tools we are developing is by collaborating with our professor from Ocean and Naval Architecture. We have the autonomous underwater vehicle. So we mount different sensors and samplers on the AUV, and this one is the Mount Explorer. That's I think the largest one, costs $1 million Canadian dollars. That's only one hosted by University and Memorial. So we're quite lucky. We also have 807 gliders, smaller type, so we can do the monitoring and the sample collection. You can basically send this AUV to the sea for weeks, so they can collect the data and send it back. Another area very important is oily wastewater treatment. So we're developing a whole fleet of oxidation process technologies, especially the enhancement measures, by using different oxidants, and from ozone to biosulfate, and also use UV, LED, visible lights, and reduce the energy, and also use different nano catalysts, and even including the metal organic framework, and also ultrasonic irradiation and biosurfactants, the AC nanomaterial adsorption. And also recently we are studying the macro reactor and using from the macro reactor to the large scale reactor. So we are trying to develop the technology targeting different waste streams, like the offshore produced water or inland produced water. They are different. And all talking about the shipping, the ballast water, bowed water, all oil spill operation, we have the decanted water. And they have different compounds and different concentration levels, and also the wastewater directly from industry, refineries, petrochemical plants, and agriculture, products like the pesticides, etc. And also we want to reduce the toxicity. This is why we study the intermediate products during the oxidation process, because one of the concerns is you're using oxidation that's very efficient to remove organics, but you producing intermediate products may become more toxic to the ecosystem. So then we have the evidence to show, the level that really depends on the conditions and how the dose of the oxidants and also the timing. So that's really comprehensive evaluation and also development to balance the efficiency and also toxicity and ensure the effort to meet the standards. And one example of application is the decanting. Because of the needs of our offshore oil and gas industry, like if you have oil spills, either minor or major, we send the vessel, carry the skimmers, use skimmer to skim the oil. Of course, you need a boom, collect the oil, and then we use skimmer to skim it out. After skimming, what you got is mixture of oil and water. So this mixture contains water from 30% up to 90%. So how to separate water and oil? The practically in Canada, all this mixture will pump into a barge in the tank, then carry them back to the shore for disposal. If you're talking about the offshore oil and gas industry, the platform is far away from the harbor, then you take hours, even days for the round trip. And so that's the timing is the most important thing in oil spill. So our technology developed, we try to treat the skimmed water, the mixture, separate the water and oil, only bring the oil back to the shore. And the water, we treat it and meet the standards and discharge at sea. So that's significantly reduced time and also the storage needs. And so we have the system, we have three components: physical separation, biodemulsifiers, and EOP, we call it enhanced oxidation process. And so basically we can remove oil, TPH level from 100 ppms to several 10 or 20 ppms, and also reduce the toxicity correspondingly. And we always, based on our study, we further up, scale up. We have a pilot scale system. Very recently, early this year, we tested in BC with the Coast Guard on their base. We test the system, and the system you see the picture here is basically physical using hydrocyclone, and then we inject chemical or biodemulsifiers, and then we use enhanced oxidation process. It's compact, so and also very efficient, and need less power, so energy consumption is quite low, and also can deal with different types of wastewater, especially containing oil, and quite wide potential. And you look at the results from the lab and the field testing, we can easily reduce the TPH level from several 100 ppm to 7 to 26 ppm. For the field trial, we use the VLSFO, that's very low sulfur fuel oil. That's the new oil required by the IMO globally. And in the near future, I think most of our ships, they are going to use this very low sulfur fuel oil. And but that we have a big knowledge gap here. We don't know, what happens after spill of this type of oil. And so we're testing using different levels, 2,000, 8,000. We can efficiently reduce them to 10, less than 50 ppm. And also Dalbate, I think Dr. He know that Dalbate is diluted bitumen, very unique product produced by Canada through the oil sand. It also a very nasty compounds and very difficult to remove them. And also we can easily reduce the concentration from 8,000 to, sometimes less than 10 ppm. IMO standard, that's 15 ppm. So we're quite happy with the results. And our government partners, they were really happy. They look forward to, commercialize this system. And another important research area is talking about the modeling. We use integrated modeling skills, and from the assessment, simulation, optimization, decision making, and try to promote and decision making, especially in real time, to support the decision makers, responders. They can make a sound decision right away in their situation room, and provide a very quick updates to the people in the field, guide their operation. The time, again, reduce time, that's the key. So we need simulation models. To simulate, if you have oil spills, we need to able to simulate the oil transport and the visualizing process, and tell people where the oil will go and how many slicks will broken into, right? And then we need to analyze the risk and the impact. Also develop some vulnerability index system to evaluate the oil spill risk levels, and based on decades, 30 years of data, ocean, meteorological, and also the shaping information, and as well as ecological sensitivity. And then we talk about the response resources optimization, because oil spill, always like BP oil spill, we're talking about 10,000 people working at sea, and from over 100 different organizations, how to maximize the use of all the resources, in a timely, efficient way. So that's always the challenge. And so our methods can help the responder decision makers to maximize the use of all the response resources, from the skimmers, boomers, vessels, people, and reduce time and increase the efficiency. Another one we're using is simulation optimizing coupling, and try to support the emergency response. And also we're talking about not only the operation process, we're talking about the impact assessment, and also individual skimming, decanting, dispersion process or operation, how to simulate the operation and try to optimize the individual operation, and then also optimize the whole system, response system. So that's the contribution what we made. Another thing is the uncertainties and also human errors that always happen everywhere. So we studied human errors and their impact in a cascade way, from the very beginning, the workers in the field, to the project managers, decision makers in the office, and also the communities, and how people react to emergency and like oil spills, and what are the impact of their incapability, like people get tired, or lack of knowledge or lack of training, and eventually the impact on the decision. So we try to quantify the impact and reduce the impact. So that's the major contribution of this research. Also, from 2 years ago, we have been developing a new facility using the AR and VR, because that's the need from the industry. They want to do, every year they spend a lot of money to do the training and drilling, and not mention the real situation. So they want us to develop something based on the virtual reality, can help them do the training. People don't need to, on the boat, they can just sit in their office and put on, the HoloLens or, the VR helmet and do the training to get the feeling of the real site condition. And also, importantly, this is a platform. They can incorporate our modeling tools into the platform and, for example, the decision making, and make people, even they can, in the situation room, in the real condition, they can make a decision using our tools. There are a few new areas we are exploring. One is the cold ocean. Because we are close to the Arctic, also Canada in northern part is quite cold. We have sea ice. So we studied how the sea ice impact. For example, here is fragile ice, impact on the oil distribution, especially the particle size and the dispersion effectiveness. And obviously, there's an impact, a negative impact. But we also compared chemical dispersants and bio dispersants. We happily found our bio dispersants, when you have a higher mixing energy, you can, offset the negative impacts. We also talk about the deep ocean, and because the whole industry moving towards to the deep. And then what happens if we have oil spill at open sea, far away from the shoreline? And we studied the oil droplet size distribution under high pressure. We have quite unique system. We can increase the pressure to 200 bars. Correspondingly, that's 1,500 meters deep. And we studied the impact of pressure. Very interestingly, we found pressure, there's no significant impact on the droplet size distribution, but the DOR, the dispersion to oil ratio and the mixing energy become more important. So that's really help fill the knowledge gap in the field. Another important area we are doing now is look at the co-contamination between oil and also emerging pollutants like microplastics. And probably it's hard to link them together. But if you look at the reality, for example, the feature showing here, Gulf of Mexico or North Sea, we have a lot of oceans, they heavily produce oil, or very basically transport oil. There are a lot of oil spills. And on the other hand, along the coast, we have cities, we have communities, we discharge municipal wastewater that contains a lot of plastics. So that's where plastic need oil. And what happens? And very interestingly, we found the mechanisms, and the oil, plastics, and also dispersion, they can form what we call the MODA, is oil microplastic dispersion aggregates. And smaller microplastics can, have negative impact on the oil dispersion. And also they can form different types of MODA. So that's still ongoing study. We published a few papers, but I think we still have knowledge gap about their biodegradation process, photooxidation, bioaccumulation, etc. Yeah, I think that's basically all, the recent research. And our vision, is for better tomorrow. And we develop cutting edge technologies, and through the collaboration, and especially the multidisciplinary research collaboration and network. And here's the network I want to introduce very briefly. That's we call the People Network. The name is, full name is Persistent Emerging and Organic Pollution in the Environment. So I name it as people. So people create environmental problems. Our people to help identify solutions. That's our slogan. So we have a very wide collaboration. Luckily, we got funding, several $1 million from the government, and to support our research, especially training. I think this network, a lot of money used for training, exchange, scholars and students. And it's growing quickly. And now we already have 200 members, more than 20 Canadian universities and 15 overseas universities, and plus 50 partners globally. And we are going to have our annual meeting conference this year. We already had annual conference in the past 5 years. And so this year in PI, and welcome to join us either in person or virtually. That's a hybrid event. Okay, in summary, so there are a few take-home message. I think we are facing growing risk of oil spills globally, from harbor to the deep ocean, and how to fight against the spills. More importantly, how to prevent them from beginning. And also, don't forget, not only the major spills, there's a huge amount of we call chronic spill or minor spill or leakage from the loading, unloading operation of ships and the products or facilities. How to deal with them, and that's especially the cumulative effect, and how to be intelligent, using intelligent, the AI tools to support our decision making, and how to reflect human behaviors in the decision making, and how to develop more green and effective technologies, and train our next generation of researchers and responders. And we need collaboration and funding for sure. Also, we should think and do outside box, jump out of the box, right? Like how to use nanotechnologies, biotechnologies, artificial intelligence, and VR, virtual realities. Those new technologies to enhance our response capacity and our knowledge. Here's a comic. I would like to use this one to end my talk. You see, the opportunity always comes with challenges. And although we are not businessmen, we don't want to exaggerate, but we are researchers and we are engineers, right? So we should develop more reliable, useful technologies and tools for the industry. We cannot stop them. But on the other hand, we can support them with better technologies, with less pollution or spills happen in the future. What we present, definitely not my own work. It's a whole team, generations of students and our professors and collaborators. So I thank them, and and also our funding agencies. Of course, next generation, we need education, better training. Okay, that's all. And at last, here where I am, that's very east part of Canada. That's the Newfoundland. Here's the St. John's. And we have very beautiful, colorful summer, you can see, and we can watch the icebergs and whales. Welcome, to visitors. Okay, thank you very much. That's all.
Thank you very much, Professor Chen, for giving us such a wonderful and informative talk. Then now let's come to the Q&A sessions. Is there any questions from the audience?
Simon, may I start first?
Okay, Professor Yang, please.
Thank you, Professor Chen. Wonderful talk, very comprehensive description of the history and also the current situation and the new technologies. I attend several of international conference and I learned from the several groups from UK and also from Korea. They seems to suggest that for the onshore oil pollution treatment, they suggest that the early removal of the oil by volunteers is the key, and then they suggest not to use chemical dispersion. They did a comparison. In actual fact, the use of chemicals didn't speed up the recovery. So they say, just leave it alone and then let the nature to do the cleaning. So that was the message I got. But they emphasize the early cleanup is the key, because you remove the mass of the oils from the site. So but today I really get to hear that you develop this the bio
biodispersant. Yeah.
Your bio surfactant and also the bio demulsifiers. So those
Yes.
have a great potential to speed up the recovery. That's very nice. So I want to hear from your view whether we should just let the nature take its course or use your product to advance it. The second question is that you mentioned the potential use of AI technology. I want to hear more in what aspect we can use AI. Thank you very much.
Thank you. Thank you. I'm glad you are interested. I think that's always an argument if we should apply chemical dispersants. I think that's one of the driving force why we developed this green solution, try to substitute partially or fully the chemical surfactants. That's true. The argument I think is the oil is toxic and the chemical compound also toxic. So because of the emergence situation, people have to choose something to remove the oil, then use a less toxic compounds to deal with highly toxic compounds. Although that's not the best solution, but the reality is the chemical compounds, the dispersants, demulsifiers already being used for many decades and approved by the government. This is why after BP spill, because in the BP spill, the chemical compound like corrected 9400, that's used over 1 million gallons. So that's really a big concern. Still now, researchers are working on the toxicity caused by the dispersed oil. And because also some argument talking about the dispersed oil is more toxic than the oil itself. So I think that the principle is the dispersants, it can accelerate the biodegradation process. That's a strong evidence there. So talking about major spills, if you're talking about really minor and also volatile compounds, maybe the nature will take it over. Even you're talking about the rough sea, like in Newfoundland, we have pretty rough sea condition. Or if you have spill far away from the shoreline, when you have the vessel reach the spill site, you could not see any spills. They already dispersed, already disappeared by the wave or by the current. But if you're talking about major spills, there are oil slicks floating on the surface. And we definitely want to remove them. As you say, I fully agree. As quickly as possible, you remove the oil from the water. That's the key. That's the most important thing. Then you can stop them further floating, especially moving towards shoreline. As soon as the oil reaches shoreline, that will be a disaster. You will have black sand, black beach. So that's caused a long term, like the Alaska one, over 30 years already still have tar balls. So this is why I think that on site, how to recover the oil is really the thing we should put more efforts. And this is why we developed this so-called decanting system, plus with the dispersants and like a bell herders. We can herd oil together and skim them out. And after skimming, we can separate oil and water, only collect the oil and discharge the water after treatment. So that will be the perfect solution. I think we are moving slowly towards to the optimum condition, but still I see it's a long way to go, because any product, like we hit the wall, like for example, our bowel surfactants. That's really good. The government, they recognize, oh, that's really promising. But any products, if will be used in the market, by the industry, in Canada, they need a long time to evaluate the safety, the toxicity, the consequence, etc. So it'll take time, frankly, until the industry can use it, in practice. And any new technology, that's also take times. That's good. It seems safe, but also not good. That delay the application, frankly. Yeah, that's true. Regarding the AI, I think that's another new area. Is booming, especially in environmental field, also including oil spills, because I can give you one example. Again, like the Gulf of Mexico oil spill. I discussed with the leaders, a few leaders from the response group, and they complained. They are sitting in the situation room because there's over 10,000 people working in the field, 100 organizations, 100 vessels, and 100 aircraft, manned or unmanned aircraft. So they every second they collect information, and from the satellite, from the people working in the field, the huge amount of data flowing into the headquarters, the situation room. How to even collection, even organize, that's a huge amount of work. How to quickly analyze them, digest them, and turn the information, the data, into decision to support the decision is a huge challenge. I think now we have very powerful computation power, along with the artificial intelligence, the new tools. We can provide a more efficient support to the decision making. It's especially talking about the dynamic, real time. I think that the AI, like our lab, we have been using AI, data mining, deep learning, and for the data analysis and also image analysis. For example, recent papers we published by a few students, they studied the microplastics and take the image using SEM, and then how to analyze SEM image using deep learning tools. That produce some interesting results. We never thought about that. So I think that's the AI tools already become everywhere. I think we definitely should welcome and embrace the power of AI.
It sounds very, very exciting. I can see our Associate Director, Dr. Leo Chen, raise up his hand. Leo, please.
Hello, Professor Chen. I'm also Chen, 我们是从中，可以听到吗
？It's hard, yeah, 不太清楚。
喂，
Good, it's better.
可以听到吗
It's better. Now it's better. There's an echo.
听不到是不是？
可以听到，没问题。
Clear. We can hear. We can hear you.
Yeah, we can hear. No problem.
喂。
It's okay. We can hear.
Yeah.
It's okay now. Yeah. I'm very interested in your MODA. So I wonder whether we can make use of your MODA to remove phytoplankton, for example, harmful algal bloom, because in your diagram you show that the MODA can accumulate the counterfactual, right? So I wonder whether we can make use of the MODA to remove harmful algal blooms.
Sorry, I could not catch the keywords.
I can repeat for him. He said your MODA can remove oil and also potentially for microalgae. Because Dr. Leo Chen is expert on harmful algal bloom. He just wondered whether your robot can actually remove the microalgae as well.
Okay. Oh, that's interesting. We have been always targeting the organic compounds, the pollutants. But because of the power of the oxidation, I understand that you're talking about the EOP, the enhanced oxidation process, right? So it's very powerful to oxidize or minimize the organic compounds, including bacteria. So because by nature, the UV, oxygen, ozone, they are very powerful disinfection products. So this is why what we have been, we're not studying the microalgae, but we have some studies regarding the bacteria, the macroalgae, because we did some research for the ABS, the American Shipping Bureau, and talking about the ballast water. So I think the invasion species, that's the key concern of the ballast water. So the EOP system can very efficiently to kill the bacteria and also for disinfection purpose and remove those invasion species. On the other hand, can also remove the like lubricant, those oil, although that's trace level in the ballast water. So I think that's a very promising technology. And more important thing is our system is compact, could be a very small footprint, customized and modular design, so can be easily fit into the vessel. Really depends on the real condition, the configuration. So yeah, I think that that's a affirmative answer. We can kill the bacteria and the algae. Yeah.
Thank you. Yeah.
Yeah. Thank you. I think one thing is we need pre-treatment. If we're talking about the large particles, we usually remove them by filtration. And then we deal with the small particles and also dissolved part. That will increase the efficiency, because if you have large particles, they may block the nano catalyst and also can block the radiation from the UV or LED or even sunlight. Yeah.
Thank you.
Thank you.
May I invite Dr. Henry He to provide some comments or questions?
Yes, thank you very much. Yeah, first of all, thanks Dr. Chen for this nice presentation, for letting us know the impact of the oil spills in marine environment. So you may know Hong Kong government is launching a new LNG project that that will bring us greener energy in the coming decades. So I think the public are somehow concerned about the potential leakage of this liquid natural gas once the terminal has been built. So based on your experience, what's your comment about this concern? So what's the, compared to the oil spill, the liquid, is it safer for the liquid natural gas? I'm not hoping a spill, but in the similar accident scale, is it safer?
That's a very interesting question. Frankly, to my knowledge, the study on the LNG and also other biofuels now quite limited, I should say. There are some, but very limited in terms of spill perspective. For the LNG, because that's with a pressure, that's liquid, and if there's spill, that's most part will be volatile or semi-volatile part. Right? So that's like our gas spill. It's relatively easier to remove, depends on the condition. If you are talking about inland in soil, there seep into the soil and even groundwater, that may stay a longer time. If you have a spill in the ocean, that basically volatile, evaporate to the atmosphere, or some remaining on the surface will create a very slim sheen on the surface, will be hard to remove. But again, I didn't study the LNG, so I just based on my understanding. I think this is why I think it's called for more research on LNG, the spill, and also talk, because I think the major part will be the safety for the responder because of the toxicity and volatile. So that's quite different, create quite different situation comparing with the traditional crude oil spill. So how to protect the responder. And that also means a shorter window for the response because of the emission quickly and spreading quickly. If you have a strong wind, and what will be happen to the community in downwind. So that's really something I think relatively new to the government industry, also for researchers. Another related issue is the renewable energy and the biofuel. Again, biofuel, the use of biofuel is growing. Biofuel itself is relatively easy because it's from the microbiology, from organic process, and they're biodegradable. But all the biofuel cannot be used independently. They're always mixed with certain level of traditional oil. That's the problem. And also the mixture, leading to different intermediate products during the biodegradation or photooxidation, we don't know yet. So that's really create a lot of unknown area. I think I feel excited because there are small things we can research. Yeah.
Here we have Professor Huang Qinghui from Tongji University. Qinghui, would you mind to speak your question? Yes.
Thank you, Professor Chen, for your wonderful sharing. I have a question. When an oil spill occurs, the way of the harm to different organisms may be different. So some are show toxic effect caused by absorption or intact of the hazard materials, and some cause biological asphyxiation of physical or physical damage. So how can we balance the protection of different organisms when taking measures to deal with an oil spill accidents? Thank you. Yeah.
Thank you. That's an interesting question. Yes, my understanding, because it really depends on the oil properties. Like I mentioned briefly, we talk about the different groups, depends on their gravity, especially, and also viscosity. I think the how to handle the volatile part and the less semi-volatile part and also heavy part. Because when you have the oil, especially during the visoring process, you are end up with different byproducts or end products, and they have quite different chemical, physical and biological properties, and leading to different level of toxicity, and also leading to different targets or receptors, and from the response or receptors perspective. I think this is why we are looking at not only the responders, the surrounding people, and also looking at the ecosystem and animals from, it depends on the inland or depends on, all that's at sea. So I think that's a whole package. And this is why I think the risk assessment, impact assessment, are always the important steps. If you have any spill, I think that's why I always advocate the modeling tools is very important, and even including, we mentioned AI. So how to very quickly understand the impact, and very quickly using the detection tools, understand what kind of spill, what kind of oil, and if that's a pure oil, if that's a combination, and also when they spill to the environment, is that talking about fresh water or brand water or seawater, and what are the ambient conditions? So that's quite comprehensive evaluation. In Canada and also North America, we're using NEBA. We call it NEBA. That's a net environmental benefit analysis. So that's a tool have been used for decades. However, recently globally, there's a new trend we call the CEMA. It's more, it's a better tool to incorporate the ecological, economic impact into not only considering the environmental pollution. We also talk about money, talk about the health, talk about the ecosystem. So that's more comprehensively evaluated the impact. So we're using that tools to screen the different technologies, different methods, and then determine what's the best combination of response operations. So then we guide the responders in the field to respond to oil spills. So yeah, I think there's a growing new tools available to deal with these complicated problems. Yeah.
So thank you, Ching Fei. We given the time limitation, we can have the final 1 to 2 questions. Especially, we welcome questions from research students, PhD students, and postdoc.
Dr. Liang, I have one question. Hi, Dr. Chen, Dr. Liang, and Xiaying. This is Shen from Shandong University. Hi.
Hello. Hi, Chen.
Hi. I think this is the second time I listened to Dr. Chen's lecture, and very impressive and always learn a lot. The research
Thank you.
Advanced and very comprehensive, I think, including experimental and modeling studies. I actually have two little questions.
Please.
One is I think there we all know that there's a high level of ions concentrations in seawater, right? So will that be an issue when you these technologies you mentioned? This is my first question. My second question is that the lab scale treatment of the oil, I think it might be very effective. But how to fix the low treatment efficiency problem when we're doing the pilot or field studies? This is my second question.
Okay, very good question. I think the first one definitely in seawater, even the the salt water, even for the inland oil production, we're also facing similar problems. The iron brine does exist, and also the more important thing, when you use oxidation, they create intermediate products, and that's the concern. Why? Based on our study, those kind of iron and brine compounds, that's the key things raise the toxicity level. But really depends on how you treat, and like for example, the timing, the retention time, and also the dose. That's why you should try to find the optimum condition. It's kind of a balance, right? Yeah. And also we try to reach the full mineralization, although it's always hard to achieve because on the other hand, it costs money, right? You need more energy. And so in the lab, we can easily achieve because we're using mimic seawater. But when we bring the real seawater, especially the seawater already have some background, the matrix, other contaminants, even metals. So that creates, more challenge. So again, the EOP, the enhanced oxidation process, it's not a magic bullet can kill everything, can solve all the problem. But in most cases, it's very helpful. And also, like through the treatment efficiency optimization, you can reduce the toxicity level and also reduce the production of the intermediate products. So that's what we reported in a paper. I think Bowel published the paper in JHM. So I think that's why we try to develop a pathway map, see different types of intermediate products based on the different conditions and correspondingly the toxicity level. And that provide a very good, clear guidance to the industry when they use the technology, right? Decide, okay, what's the best level of the dose, what's the best timing, for the treatment and also retention. And if needed, should we add in a post-treatment, for example, a membrane or maybe absorbance? So the all helps. Yeah, that's your first question. The second one, you're talking about the pilot and the field trial, the relatively low efficiency. That's true. That's always, I think, that's a long-term headache for all the researchers when they scale up their system, especially before the commercialization. You have a perfect results in a small scale. When you scale up, then there's different problems come out, right? So it may come from the design itself, because it's enlarge the small arrows, and just like the uncertainties or arrows, right? It's a propagation process. And so that's back to your design. Look, you need to review, what is the problems, and also there's some operational issues. Even just like in our field testing, I experienced a lot. Sometimes the whole day is just mess up because there's a leakage, a small leakage from a pack. You never thought about that, right? So because of the glue. And so I think another key lesson I learned, we are researchers, we are very good, we are very confident in our technology, our methods, our system, but we still need to rely on the technicians. You should find a very good technician. They can save you a lot of time and money. They know which parts fit to which condition, valve, or pressure, flow rate, right? They can quickly tell you, okay, this is the best glue for sealing, right? When you have a high salinity, you have acidic solution, right? So that's something we don't know. But that's my tip. You hire a very good technician, really helps. And also, I think another thing is from the scaling up, like one of our team is doing how to model the scale up, especially how to simulate the process. Then using mathematical models, even using AIs, we can help simulate the whole process and based on different scales. And then you can easily to find the problems when you scale up using numerical models. And then based on the results, you revise your design, you readjust your configuration, and then bring that to the field for testing. Yeah, but there are always problems when you do the field test.
We can try to fix them.
Sure. We always have solutions, right? We are engineers.
Okay. Thank you, Chen.
Thank you.
I think last time I saw you and Dr. John is 2017.
Oh yes, long time ago. I know.
Face in the near future.
Sure, definitely. I look forward to getting together again.
Bye.
Thank you, Professor Zhao and Professor Chen. And I think we still have many questions here, but time is up. I have to skip to the end. If you still have questions, you can contact Professor Chen personally through email. And I really appreciate the wonderful and informative talk Professor Chen gave us today. We expect more opportunities to talk to Professor Chen. I appreciate the Sticky Lab of Marine Pollution for launching this distinguished lecture, and also thank the Department of Chemistry for helping organize the event. Thank all the audience for your time and active participation. We look forward to meeting you again in the next distinguished lecture. Have a great day. Goodbye.
Thank you very much.
Thank you.
Appreciate it.
Thank you.
Appreciate the
Thank you
invitation
very
and
much.
also the opportunity. Thank you.
Thank you. Thank you.
Thank you.
And welcome to visit me.
Yes.
Bye-bye.
Bye bye. Bye bye.
Bye bye.